this is Pre-Calculus Concept 21b. We're going to once again be solving exponential equations, but this time using a different method. So instead of like bases, we're going to actually use logarithms to help us solve exponents. There's basically 4 steps for this type of problem you want to remember. Step 1 is to isolate your exponential expression. Sometimes that'll be done right off the bat. Other times you'll have to do a little bit of work at the front end of the problem to get the exponent part on one side of the equation by itself. Step 2 is going to be to log both sides of the equation. That's going to be a key step. We'll talk about that through a couple of examples. In step 3, you want to simplify, and we want to go back to remembering some of our properties of logarithms, just a couple that we've talked about. If you have log of b to a power, that power can be moved out in front of the logarithm. Hope you remember that one. Also the inverse properties, so if you have the natural log of e to the x, you just get x, and if you have the common log of 10 to the x, you get x. So those are going to be useful properties in simplifying. Once you have a simplified expression, you're going to see once again you have some easy Algebra 1 type problems to solve, and again, always a good idea to check your answers. Alright, let's go ahead and look at an example. I'm going to solve 4 to the x equals 15. One thing you may notice right off the bat is there's no way to write a common base here, right? 15 isn't a power of 4, it's not a power of 2, and so we're kind of stuck if we tried to solve this one with a common base. However, we can use the steps on the previous slide to solve this problem. So I want to isolate my exponent first. That's actually already done for us. The next step is to take the log of both sides of the equation. I'm going to use natural log for this example, but it turns out that you can use any log you want, and it doesn't matter, it'll always work. So we'll use natural log and see what happens. You do want to use the same log on both sides. Alright, in simplifying this expression, I want to remember that that exponent x can be moved out in front, so this can be rewritten as x times log 4 equals log 15. And then I want to solve. Some people get tripped up by this, but log 4 is just a number, so you treat that just like it was 7 or some constant, and log of 15 is just a number. And so if I want to isolate x or solve for x, it's really just a division problem. So it's log 15 divided by log 4. And each of those are decimal answers, but I'm going to pull out my calculator and evaluate that. And you get about 1.953, I'll call it. And this is definitely an approximation because logarithms have oftentimes irrational numbers with a lot of decimals, and so this is an approximation. When I do my check, it should be the case that 4 to the 1.953 is about 15. And because I rounded my answer, you're not going to get exactly 15. But you could plug it in and check and see that it should be pretty darn close. And so this turns out to be 14.991. And so I get a little bit of error there, but I can see that I've got a pretty good answer. A lot of times you could leave your answer as a logarithm. So that actually is the true answer. And then this answer is an approximation. Okay? Turns out that you can use any base that you want. So let's look at the original problem again. Let me do it in a different color. And just talk about maybe a slightly different strategy that yields the same result. So 4 to the x equals 15. You might think that using the same base in your logarithm that the exponent is written in would be something that's kind of helpful, and in fact it is. So if I have 4 to the x and I use log base 4, we can use our inverse property and realize that that's just going to be x. So another answer to this question would be log base 4 of 15. And from our change of base formula, we remember that that can be rewritten in any other base that I choose. So this could be log of 15 over log 4. And so we see we get the same answer with a slightly different approach. So turns out you can use any log you want when you log both sides of an equation, as long as it's the same on both sides. Alright, let's look at a couple more examples. I'm going to do these a little bit faster, but once again we have exponential expressions and we want to solve. This is a particularly good one to think carefully about a base that would be advantageous. So in this case, my exponent is in base 10, so I'm going to use a common log and take the common log of both sides. And when you get the left side of the equation, you have log base 10 of 10 to the x. Those are inverses of each other, and you get x as your answer. When you take the log, and I forgot to write that in, sorry about that, but I should have a log here. You get log of 120,000, and that is your answer. If you're not comfortable with leaving your answer in that form, or if you're asked to give a approximation, you can go ahead and type that in on your calculator. You have a log button, and it turns out to be 5.079. Okay. 2 is an example where it's important to remember that isolating the exponent first is a very important step in this process. In our previous examples, we didn't have to do that. But in this example, our exponent is the e to the 0.03t part, and I've got this 100. If you take the log of both sides, it gets a little tricky, and so the very best thing to do is to isolate the e part first. So I can do that, hopefully you see, by division. And so the e to the 0.03t is actually equal to 5. In this problem, I'm going to use a natural log. Hopefully you see why. Again, any base will work, but the natural log will be particularly helpful because that's going to give us a expression over here that's the natural log, so log base e of e to the 0.03t, and that just simply gives us the exponent 0.03t. The answer to that is log 5, which is just a number, and so if I were solving for t, the exact answer is log 5 divided by 0.03, and if you wanted to know the approximation for that number, sometimes you'll be asked to do that, that's going to be approximately 53.65. Okay, one more example. This one has an exponent on both sides of the equation. It's a little trickier, but you're going to use the same process. So I'm going to take the log. In this case, I'll do natural log, but again, it could be any log you want, of both sides, and that's a 2x plus 3. I'm going to use the property this time that log of something to a power can be rewritten as the power rewritten as a coefficient, right? So I end up with x minus 2 log 5. And this one becomes 2x plus 3 log 4. Now I've got some work to do in this problem, but remember that log 5 is a number, and you're going to treat it as such. So in this left side of the equation, I would distribute. So I have x log 5 minus 2 log 5. And on the right side of the equation, I have 2x log 4 plus 3 log 4. Things start getting messy. A lot of people want to pull out their calculators and get decimals for all this stuff, but basically you want to look for your like terms. So in this case, these two terms are like terms, and put those on the same side of the equation. So I'm going to write x log 5 minus 2x log 4, and then the other terms I'm going to move to the other side. So you have log 4, 3 log 4 plus 2 log 5. I can factor over here, and I get log 5 minus 2 log 4, and the right side is going to stay the same. And then I'm actually just one step away because everything on the everything on the right is just a numerical value of some kind, and everything on the right is just x, on the left rather, is just x times another numerical value. So my answer for this problem would be 3 log 4 plus 2 log 5 divided by log 5 minus 2 log 4. Okay? You can leave your answer like that. There's some properties you could use if you wanted to clean that up. Most of the time you're probably going to evaluate that on your calculator, and so you could pull that out, evaluate, and get your final answer. Okay, so it gets a little complicated there when you have exponential expressions on both sides of the equation, but you can see that idea of logging both sides works. Alright, let's do 2 U-tries here. See if you can solve this one using the idea of taking the log of both sides. Alright, you can use any logarithm you want here. I'm going to go ahead and use log base 5 to take advantage of that inverse property. So log base 5 of both sides of the equation gives me on the left side x, and on the right side log base 5 of 135. Okay, that's your answer. All of the options you had were decimals, and so I need to remember that I can evaluate that. You could use your change of base formula here if you wanted to. We also talked about how to evaluate logarithms on your calculator. This is approximately 3.05. Try the second one. Alright, with base 10, it's helpful to use common logs, so I'm going to do that. And my answer this time is just going to be log 8,000. This time your options were all logarithms, and so hopefully you chose this one as your answer.